Okay, our next speaker is Rian Dutch, who's the product strategy manager, Geoscience with Datarock. Now IMDEX, so he's got his IMDEX hat on as well now. And Ryan's going to be talking about computer vision and rock imagery, making the most of core imagery, chip imagery, and Televiewer. So I'd like to welcome Ryan to the stage. Thanks.
Okay, all right. As I said, product strategy manager at Geoscience. So what I'm going to talk about today is a little bit about computer vision, how we use computer vision to extract quantified data from images and rocks, and hopefully what the future holds for us to be able to integrate these data sets together to go from data to knowledge and then make better decisions downstream. So I'm going to talk a little bit today about how we log versus what you can do with computer vision, talk about rock imagery, and then talk about some of our products, so Datarock Core, Datarock Chip, and then maybe something about what might happen in the future. So computer vision. Everyone here knows about AI. I'm sure you've all used ChatGPT. Computer vision kind of started it all. One of the very first deep learning approaches created way back when. It's a subset of machine learning and artificial intelligence, but what it's really about is extracting quantified information from images. So using a computer to understand something about an image, and then from that, learn something about that image that we can then use to make decisions or to classify things, to be able to use that in a way downstream. A bit of a comparison, I guess, about the way we log, and I think to be clear, what we talk about here is definitely not about getting geologists out of a core farm. We're not talking about geologists not looking at rocks. Geologists do need to look at rocks, but there are things that geologists can do, and there are things that machines can do much better to make the geologists a lot more efficient and more consistent and better at what they do. You know, when a human looks at a picture, you have all the advantages of context, the background, the setting of that image, something about the rock, you know where you're drilling, you know the things that you're expecting. We can adapt easily. If you're well trained, you can be accurate within a certain area, measure of uncertainty, but we're very good at filling in the gaps. And computers can't do this. Computers are very literal. They do what you tell them to do. So they have to understand explicitly what you are trying to get to. So they have to be well trained, which means you need good training data. But there's some advantages. They can scale. You can do this at scale. You can analyze images, thousands of images in a minute, in hours, compared to logging holes, which might take days or weeks. You can train these things to do very different things, so they're flexible. And one of the really key things is they are consistent. You are consistently getting similar results. And even if the model is wrong, they are consistently wrong, so you can calibrate for that. So I guess these are kind of the key factors that we want to introduce by using machine learning to help augment the processes in the core farm, help augment looking at rocks, because it means that we can actually start to be consistent. Now, I don't know, there's probably plenty of geos in here, and I'm sure you've all been out and you've all logged core, you've all logged chips, and then your mate next door has logged those same chips and he causes something different. Now, that's a problem that we can never get away with, that human drift. But by introducing these techniques, using machine learning as an approach, what we can do is we can actually make that consistent. So we can make things consistent across rigs, across projects, across sites, so that what the results on one rig are the same as the results on another rig. And you can trust those results because of that. What those results mean still requires a geologist to come in and interpret and put the geological understanding into it, but they can be certain that they're looking at apples and apples instead of trying to compare apples and oranges with, you know, two geological logs. So let's talk about core imagery. Core imagery is ubiquitous in the industry. Everyone collects it, and very few people use it effectively. Most people collect it, store it on some hard drive somewhere, or they stick it into a Margo. They might look at it, but they don't actually use it as a data source. So at Datarock, we, the founders especially, had this vision that this is a hugely underutilized resource. There's a huge amount of information that you can extract from a rock image. It's just a matter of being able to build the tooling around it to do it and do it well and consistently. One of the key things with that though is, and you would have all heard the adage, garbage in, garbage out, data quality does matter. It's amazing how you can get away with especially in geotechnical, the geotechnical space, you can get away with some bad images, but you want to think about how your data is prepared. So the process of using something like Datarock Core is quite simple. It fits into a regular workflow, and it really does start with getting good, accurate data at the rig, taking good photographs, so using a standardized approach to collect your data, making sure that core is marked up correctly. Use your IMDEX to get the orientation mark right. Get that orientation mark on there, because then we can use that to extract true oriented structural data from your images. We can then use the software to take those images, pull that into Datarock Core, run a bunch of models, both for geotech and geology, depending on what's the models trained for, what you need to get, what your problem is you're trying to solve, and extract results within minutes to hours, as opposed to what might take a geologist hours to days to weeks to log, a very long hole. So when we talk about computer vision, we kind of talk about, we're thinking for sort of 4 flavors or 4 approaches, the information that you can actually extract. So in this image here, we've got classification on the left. That's, is this rock, or does this contain a vein or not? Is this a granite or not? Semantic segmentation, that's when you start to identify features in it. Show me every pixel that is within a feature. Detection, show me every instance, put a bounding box around every instance of a vein in my deposit. And then instance segmentation, where we can actually start to say, tell me how many pixels are in this vein, and then is this vein the same as that vein? And tell me how many pixels are in that vein. Using these different approaches, you can get different information, and we combine all of these together to be able to produce multiple results at the end. So a few examples of that here. The one at the top here is a segmentation looking at fibrous mineral detection. So this was a company who had an issue with fibrous minerals. It was obviously a safety issue, and they wanted to know, before anyone goes in there and looks at that, can you please detect all of the fibrous minerals in this rock so that we know which trays we need to be careful with and not look. And so we were able to build a model, a computer vision-based model, to identify all of those regions within minutes. This is an example here of grain size classification of pegmatites. And on the right, we took a look at one at phenocryst segmentation. And that was actually a project done to try and identify phenocrysts of different types, and then analyse the shape of those phenocrysts to understand something about the depositional setting, the intrusive setting of those volcanic rocks. Image segmentation. This is where things start to really shine. This is an example from a gold system where they had a number of different types of veins that were different mineralogy. They looked different, and I think this is a key thing. We are talking about imagery here, so there has to be a visual difference. They looked different, and they were associated with different styles of mineralization, different mineralization styles, or mineralization or not. And they wanted to know, can we detect where each of these vein types are? And so we built segmentation models and are able to detect all of those veins across an entire deposit. So something that would take a human logger a lifetime to do, when we're talking centimetre scale resolution logging of veins in a gold system, you can use computer vision to do it in a matter of days. Another example in the gold system is classification of different quartz veins. So this was an example where they had inconsistently logged these different quartz veins, but they knew that they were associated with gold in different ways. And they wanted to know, could we map these and differentiate these across the entire deposit? And so going back to a historical data set, running this process across tens of thousands of images, building up a spatially located classification model showing every 5 centimetre piece of rock in that entire deposit and where those different vein classes exist. Chips. I'm sure many of you have sat on the back of a dirty RC rig, sieving chips and then trying to make a log of that. And I'm sure many of you have been in the situation where those logs have come into you and you've thrown them out the door because they're totally useless, because they are completely inconsistent, they don't contain the right information, and they're basically a mess. We think that this is actually a huge missed opportunity. There's actually a significant amount of information within those chips if we can extract that information in a consistent way. Wow, I'm going to have to speed up that orange light came on fast. Similar to Datarock Core, the workflow is fairly simple. Take your chip photos. We have models that will extract the trays, extract the compartments, and then from that, extract every single grain and pull out information like color, morphology, shape, all of that from those chips. We can then start to use things like unsupervised machine learning approaches, where we can use the computer to say, show me all the things that are similar in that computer vision space. So they'll have similar colors, similar texture. Show me all of those, and we can begin to pull that out. And this is where you can then actually start to become predictive. Being able to use this as a way to generate essentially a pseudo log that you can then, as a geologist, come along and say, okay, I understand what this is, what this is, what this is. I can now build consistent geological logs extracted from RC drilling, chip imagery, and you can do this consistently across the entire project. The outputs of this are essentially a pseudo log, but the beauty of this is that the next thing you can do is then build a supervised classifier. So you can then take this information where you see that there is differences, build a label set from this, have your geologist come along and say, yep, this is lithology A, this is lithology B. Train a model so that on the next runs, the model tells you what rocks you're in. And you can do this off the back of the rig. You can process this within an hour of drilling a hole. I can skip over that because I'm going to go. So. All right. So that's just two machine learning products that not only produce results on their own right, but they also produce additional data. They produce machine learning ready data that you can then combine with other data sets. And this is where the power really becomes obvious for machine learning. As geologists, it's easy for us to look at different data sets independently. We can interpolate across them and make choices and decisions. But with machine learning, with these data-driven approaches, you can actually integrate these data sets together across scales and at scale to derive new insight. And so the power of this is you can then start to look at a rock and you can get information like rock texture, which you're getting from imagery, combine that with, say, mineralogy or chemistry from assay, mineralogy from spectral data, FTIR, and all of a sudden you've actually got all of the components of that rock to help you understand how that rock will behave. How will that rock behave, how it behaves in the deposit, but how it will also behave in the mining value chain as you pull that through from the mine to the mill to the smelter. And so it allows you to become predictive much further upstream with all of this information combined. And this is something that we see as the real future opportunity for Datarock and for IMDEX is to be able to take all of this multimodal information from downhole sensors, from imagery, from lab assay, integrate that with some of the other products. And we talked about Crux this morning with their measure while drill, right? That's another vital data. That's another data set that tells you something about rock properties. Integrating that with the imagery, potentially with Televiewer data, something like that. Being able to then productionize that. So Datarock has developed composable machine learning pipelines that allow us to build scalable machine learning workflows at scale really quickly, develop these and make them tailored to deliver the results that you need to address the problems that you have. So not a one size fits all, but actually these are the data that I need to solve the problem I have in my deposit. That is the future. Right now, though, we are really, really excited because we've actually already started doing this, but now that ALT has come into the IMDEX fold, there is a huge opportunity to be able to take our skills in computer vision on chips, on core, and start to look at things like Televiewer data. One of the biggest pain points that we hear from Televiewer data is the time it takes to process that data, to extract geotechnical structural information from Televiewer data. So using machine learning approaches, we hope that we'll be able to accelerate that process, reduce some of the false positives, and potentially be able to produce classified structural logs from Televiewer data, potentially from the tool to you really, really quickly. So this is a work in progress. We are actively developing this now, and we're actively developing custom machine learning model architectures and loss functions and things and building a training data set to address this problem. And this is a couple of examples of things where, it's not there yet, but it's coming. And I think that over the next 6 to 12 months, this is going to be the next big thing for us. And that is it now, the red light is flashing. Thank you.
That's excellent. Thanks very much, Ryan. And I think it's really exciting to see where this goes from here. And the DataRock guys have great skill in this area. So watch this space.